So today we're going to hear Tom's exciting literature about Erdős and Hajnal.
Thanks for having me again. I'm glad to be back. Right, so today my plan is to talk about, to tell you a little bit about the problem of finding some sparse structures. How do we embed them in graphs when we only give an average degree? So I hope this is the plan for today. We start with some basic results in this direction on cycles. I will also talk briefly about topological minors. Then I will say that what's the connection between these two using expanders. So this is our plan. Okay. Now the cycles, right? So I start with the most basic thing. The first topic, cycles. So well, cycles is just a set of vertices that can be ordered cyclically such that we have consecutive vertices being adjacent. And I will always use n for the number of vertices in my graph, in the host graph. By host graph, I mean that's the graph in which we want to embed the structure we want to embed. So the first result we learned in graph theory is that if we have an n-vertex graph, how many edges needed to force a cycle, right? Then we know that if you have at least n edges, we have a cycle for sure. This is best possible if we at most n-1, it could be a tree. So we are not guaranteed to have a cycle. I would like to reword this fact in this language. I write our graph G. Average degree is the sum of the degree of the vertices divided by n, which is also 2 times the number of edges over n. So this fact can be rephrased as whenever I have average degree at least 2, some constants, independent of the order of the graph n, then I know there is a cycle. But I will write it as C sub g is non-empty, where C sub g is a subset of the natural number containing all distinct cycle length in G. Okay? So let me define it to be the set of cycle length in G. Well, we start with this basic fact. We all know this fact, and it basically illustrates the feature of this direction of research, meaning that when we're given average degree, what sort of structure we can guarantee to have? What structure if large average degree force you to have? Okay. So let's continue and see here. In a sense, it's less satisfying because all we know, if it's exactly 2, it could be that we have a Hamilton cycle. That's the whole graph. So we just know that there's one element in here, a singleton. Not so satisfying. Can we have a richer set, right? The first question possibly come into our mind is, can we have a specific number? Okay, instead of some number we have no way of controlling. Can we have 100? Can we have 1,000? Can we have 1,000,000 lying in this set? Okay. Question. Let's say the host graph is connected. Yeah. Otherwise, you can look at the components and look at its average degree there.
We also consider what graph?
Let's say we all consider simple graph. Yeah. We might as well. Right. Yeah. Let's look at simple graphs. And by looking at the component, we may assume that it's connected. Yeah. So now, right, so the theme, here's the theme, is that basic question. If we want to extend this basic fact, if we have large average degree, the question is, what cycle length can we have? Do you know anything about this set C of G? Can you say anything about it? Okay, so let's see some examples of this sort. First of all, we cannot guarantee any finite set. So if you pick your favorite number, that's not guaranteed. Oh, I have to make this more precise. So more precisely, what does this mean? Force a cycle length. What I mean is that you can force a length to be a cycle length if, more precise, if there exists the absolute constant C, such that when your average degree is bigger than this absolute constant C, sufficiently large, then for sure you can find this cycle length in the graph. Okay, that's what it means precisely. There exists a constant C such that for any graph G with average degree sufficiently large, but notice that it's constant in a sense. We should always keep in mind that in this talk, usually I will consider anything independent of n, the order of the graph, to be constant, and n is some quantity tends to infinity, let's say. Okay? Then we can get certain length. Okay, more precisely, this is what I mean.
Like at least a certain length, or
exactly, exact length. Yeah, I want to know how elements in C of G look like, sort of. Yeah, what elements lies in C of G?
what do you mean by say get certain length element? It's C of G. The C of G is always the length of the set.
Maybe more precisely, force certain number to lie in C of G, maybe. Okay, in that sense. In other words, when you have sufficiently large average degree, we must have this length as a cycle length. Yeah, you can find the cycle in your graph. So, we have to start with the negative news, right? Let's pick a singleton. You pick your favorite number, 2020, right? We cannot force this number, right? Any number, in fact, any finite set cannot be forced, cannot be guaranteed by large average degree. Okay? So I'm not going to make this statement precise. I'm just going to say it in words. What it means is that there exists a sequence of graphs with growing average degree to infinity, such that none of which contain any elements in here, in this finite set, as a cycle length. That's what it means precisely. So why is that so? This is famously proved by Erdős back in 1959 by his one of the early applications of probabilistic method, showing that, so Erdős using the probabilistic statement constructed the graph with arbitrary large chromatic number, yet arbitrary large girth, right? So there exists probabilistic construction, a graph G with two property, large chromatic number and large girth. So that means what? This in particular means if you pick your favorite finite set, let's say finite set A, if you fix A, what I can do is I find the maximum element in A, that I made the girth larger than A, right? Then why this guy has large average degree? Because when you have chromatic number k, you can make it k critical, chromatic critical. So it has degeneracy k minus 1. It contains a subgraph that has an arbitrarily large average degree, right? So chromatic number is a stronger condition than average degree. So that's the first piece of negative news. We cannot force any of our favorite finite sets. So no finite set. Okay. Then now what lies in front of us, the two natural directions suggest itself. What are the two natural questions now? If we cannot guarantee any finite set, can we say anything about the density, whatever defined in the proper way, of C of G in N? Given that its average degree is sufficiently large, okay? Second question, again, now if we cannot get finite set, what about infinite set or infinite sequence? Can you hit some elements in this infinite sequence instead? That would be another natural direction. So one is about how dense it is distributed. Another one is that can you get some specific element now from an infinite set, right? Okay. Any questions so far? Yes?
Do you mean by this first certain element, line CFG? Is a certain element, according to this next sentence, any finite set?
Yeah. You pick a set you want to realize as a cycle length in the graph. Now you can ask that for this particular length, can it be realized when you have a sufficiently large average degree? Like you pick, say, 8, yeah, and say, now my average degree is a billion. Can you find the length of cycle 8 in any graph with average degree a billion? The answer is no, right? By this construction. Right, yeah. So
when I compare this with your second question here, this guaranteed, you mean when you have a finite set, you cannot force this to be a subset of C of G, I understood, right? But,
no,
They completely destroy it.
point. None of the elements is in C of G. Yeah. Mm-hmm.
That the G intersected with some given set is non-empty.
right. So that's what guaranteed means.
Right. Yeah, in a sense, here I a little informal. By guarantee, I means that when my average degree is sufficiently large, we for sure will see a cycle, right? You will see. Well, how do you prove it? And if you have to prove that for sure you will see something, then you have to be able to embed it using large average degree. Yeah? So, okay, that's the. So after Erdős negative result, these two questions seems natural, but we have to make them rigorous. Okay, so let's first look at the first question, for example. So back in 1966, Erdős and Hajnal, they suggest a way to measure the denseness by looking at the harmonic sum of C of G. Okay. So that's how. So for the first question, they say that how about harmonic sum? In particular, they conjecture that if you look at the cycle length, in your graph G, it diverges together with the chromatic number. Okay? So this is, for example, a way to measure the denseness. And in fact, this conjecture has been confirmed. So it is true. It's proved by, after two decades, in 1984, by Gelfash, Komlosh, and Samaradi. So what do they prove? They prove actually something slightly stronger. They say that we can replace this kind of, we don't need the chromatic number. As long as your average degree is sufficiently large, then the harmonic sum of the cycle length diverges. So their statement reads as follows, that the sum of the reciprocals is linear, at least grow linear in the logarithmic of the average degree. Okay? And I would like to make a remark that this is optimal up to this implicit constant here by looking at, for example, KD or KDD. Okay? So if you look at, I would like to take KDD. So this guy has average degree D. You have all cycles from 4 to 2D. And if you compute the sum here, this is 1/2 plus minus little 1 times log D is the harmonic sum here, right? For this example. So the order of magnitude of the growth here cannot be improved, for example. So in a sense, it's quite satisfying, the results. But that leaves more questions, in fact. Before they actually proved this, Erdős already asked whether this strong bond holds. So they later proved this weaker bond. So let me write down Erdős' question. So he's conjectured that, in fact, we should have 1/2 here. That would be the structure. Okay, let me write it. This is in 75. He asked that, is it 1/2? Meaning that whether this KDD is sort of the one minimizing the harmonic sum. I want to point out a local obstruction here, meaning that if we only given the average degree rather than chromatic number, we cannot force any odd integer as cycle length, because the graph could be just bipartite arbitrary large density. So that brings us another question. That's the question of the title of the talk, the question raised by Erdős and Hajnal, saying that if we consider, since this even number is easy to force by average degree, now what if I have the chromatic number tending to infinity, but you only consider odd integers in here, that they still diverge to infinity? That's the Erdős-Hajnal's off-cycle problem. Okay? Because of this local obstruction, average degree doesn't do anything here for the off-cycle length. So I will use C sub O of G to denote all the odd integers in the cycle length. Okay, does this diverge as the chromatic number diverge? So already we have two open problems. One is what about the more precise result here, and one is what about the a result about off cycle length. Right. So now I would like to talk a little bit about the second type of problem, about the infinite set sequence. What do we know about the infinite sequence? So we know any finite set, we cannot force it. Infinite sequence, Erdős has some of his favorite sequence. I think it was gradually asked in the 80s and later also yes. In fact, he offered $1,000 for this infinite sequence, but there's no way that we can claim the money. But so the infinite sequence in particular he's interested in is what about power of 2, okay? So can power of 2 to the I, be forced by large average degree? Okay, again, the formal statement is, does there exist an absolute constant C such that for every graph whose average degree is bigger than C, you can for sure in this graph embed a cycle whose length is power of 2. I don't know what's I, but some power of 2. Okay? Or C of G intersect this infinite sequence, if you'd like to say that. But this was a little bit difficult, so he suggests some much slower growing sequence. What about, say, the I prime plus minus 1, for example? There's other much slower growing, or a perfect square. This kind of, there are plenty of sequence that he was interested in, something like this. So let me just leave it like that without further comments. What kind of infinite sequence some people were interested in before. So so that completes the first part of the talk about the cycles. We've seen some. Maybe here let's do an interesting exercise about forcing some infinite sequence. I think it's a Q exercise. This was a result about forcing infinite sequence by large average degree. It's proved by Warwick in 1977. That answer in particular itself a question of Bohr and Erdős, I think. They were asking if I take the sequence to be an arithmetic progression containing even numbers, can you force something in this arithmetic progression? It has to contain even number, otherwise all odd. Average degree cannot force any odd number. This is a nice example we can do. So Warwick, for the second type of question, shows that for any arithmetic progression with even numbers, we can force it with average degree. So I'm going to prove a weaker version, very cute proof. A weaker version is what? Let's suppose this sequence it's homogeneous in a sense. So let's say this sequence is A times D. Let me use step length K. Okay, for all different A. Suppose this is my arithmetic progression with starting point 0 instead of having another plus B. So let's prove this special case. This is very easy to prove. So what we so it has to contain some even number, infinitely more. Because the arithmetic progression could be 1, 3, 5, 7, right? But this arithmetic progression, we cannot force any elements in there because I can take complete bipartite graph with growing average degree. It doesn't.
If you want to force some set, you can always. It's enough to prove for subsets, right? So
yeah.
Whenever you have an arithmetic progression with evens, then you can take subsequence to.
Right. You can also say just pick a different way of phrasing it. I think wouldn't be too much different. Yeah. So suppose we have an even number in there, or you start with the pure even number. It wouldn't be too much different. So what I want to show is this simpler version where we don't have plus b. Suppose our number is just like, I don't know, 5, 10, 15, take k equal to 5, right? So how do we prove that k equal to 5, and you have sufficiently large average degree, you can force a cycle length that's multiple of 10, because we want to force even number, right? Okay. Can you get 10 or 20 or 1000? How do we prove that? Here's the proof. So he actually used a result. It's also related to the second topic about the minor, topological minor. So what is topological minor? Basically, if I draw a K4, this is K4. A topological minor or subdivision is basically any graph you can obtain by subdividing replacing the edge by a path, such that all internal vertices are disjoint. Okay? You might just leave it empty. You don't have to subdivide it, or you can subdivide anytime you want. Any graph obtained this way is a topological minor or subdivision of the original graph. Then there is a result by Mother who showed that for any t, there exists d, which is a function of t, such that for any graph G with average degree So Warwick basically used this result of Mother, who showed that if you want to force a clique as a subdivision, give me the order of the clique T, then constant average degree is enough to force a clique subdivision. Okay? Now the remaining proof is very cute. You have your T clique subdivision here. You take T sufficiently large. Now for every edge, you can find the residue mod K. So every different residue represent a color. Apply Ramsey, you find a monochromatic clique there. And you make sure that this monochromatic clique is sufficiently large, then you take enough cycle, you can hit anything in AK. Okay? That's the proof. Yeah, that definitely is not a good bound. I haven't thought about it. Yeah, because it's you first apply that, then you do Ramsey, the number grows like crazy. Yeah, I think. Right. So the second thing I want to just give a touch on that. I don't want to emphasize too much. Is a topological minor subdivision, which I've just defined. So I'm not going to give a formal definition. I don't want to spend too much time on this, but I would like to mention two results, one of which I've already mentioned. This is one of the first extremal type results of forcing a clique subdivision. So what's interesting about this is that by Thomasen's theorem, to force a clique as a subgraph, you need positive edge density, quadratic number of edges, which grows crazily with the order of the graph. But to force a subdivision is much easier in the sense of average degree. Constant is enough. And another historical result, maybe I should mention, is Kuratovsky's theorem, which kind of the starting point of the study of subdivision that characterized the planar graph. Right? A graph is planar at 1930. That a graph is planar if and only if there is no K33 or K5 subdivision. And later there's this graph minor project by Robinson Seymour, but that's different direction. I would like to talk about this direction, the extremal direction. So here, so someone talk about the quantitative thing. D of t. What's d of t here to force a kt subdivision? Original proof is exponential in t, and there's a conjecture that quadratic in t suffices, and this was confirmed. It was a conjecture in the 60s. After 30 years, it was confirmed in the 90s by two groups of people, Bolobash and Thomassen, and independently Commerce and Samarady. They showed that when your average degree is bigger than some absolute constant times t squared, then you can force kt subdivision. And I leave it as exercise to think why t squared is the optimal bound. You cannot go below quadratic bound. Okay? So here there's a cute problem that I personally quite like by Carsten Thomassen. In 1984, he asked a strengthening of this extremal type result in a different direction. He asked that, okay, we know that constant average degree is enough to force a clique subdivision of any given order. Can we have more feature of the subdivision? The feature he was asking for is that every edge is subdivided equal number of times. Here in particular, we have no control on how edges are subdivided. Right? Just know there exists one. So let me write precisely. Can every degree force that? Means, does there exist constant C such that for every G with every degree bigger than C, then G contains, and let me just say, equally divided. Okay. For any T, C of depends on T, such KT subdivision. Okay, this is the question. Is it clear, the question?
But here, when we ask about equally divided, we don't care how often. It's just that it's equal.
Just that it's equal. Yeah. Right. How often we cannot force it? Because of the Erdős construction, finite sets, right? We can go beyond the girth, yes. So just give one board on a touch on this type of problem. I think I've talked about this in more details before, but today this is as much as I want to talk about. So now we bring us to part 3 and we can conclude. Part 3 is this smiley face at the end, the expander. So why I mentioned these two seemingly completely unrelated results? Because basically all these open problems that I mentioned, we managed to resolve all of these, confirm them, and this is through expander. So I'll give a little bit time. I'll talk about the expander. So probably we're all familiar with expander, but let me just give a quick intro of what is it and why it's important, just so that we're on the same page. This is another fundamental notion in graph theory. It was first introduced, I think, in the 70s by Pinsker. Right. Introduced back then. So we all know that graph can be used to model networks. Okay, but a lot of the time, well, I'm not in CS, but when people do computation, where the graph is very dense, that's not good. Okay, if you want to connect cities, but too many roads, that's too expensive. So you want the sparse network to connect, to reach everywhere efficiently. So this is one of the original motivation of expander. Can you come up with a graph that's sparse yet highly connected in a sense, small diameter or whichever you want to put it, right? So in its essence, this is a graph that's sparse and highly connected. I'm not going to make this too rigorous, okay? Highly connected, okay? Then there are two types of meta questions about expanders we can ask. One is, how can you construct the expander graph in whatever expansion sense you define? How can we find one? Second question is, what can we do with them? Right? Two types of meta questions. I'm going to focus on the second question. What can we do with them? But let me also just point it out that expander is also interesting, reflected by the fact that it can be defined in many different directions, ways. Okay? Just very quickly, in the graph sense, or combinatorially, or geometrically, you can see it, is that a graph is expander if every vertex set has a large boundary, meaning that if you look at its neighborhood, n of x grows proportionally to x. Okay? Expander. It can also be defined probabilistically. Okay? How do we define it probabilistically? On any graph, we can perform random walk. And then expander are the graph that reaches the stationary distribution the fastest, called the fast mixing property, right? You can also define it linear algebraically by looking at its adjacency matrix and see if there's a spectrum gap. Okay? So already from this fact, we can see that it has connections to many different branches, and different tools can contribute to the growth of this notion.
It's a graph which is sparse and highly connected in, but
yeah.
But the complete graph is in Spanish, surely.
Yeah, but it's not sparse, right? Complete graph, right? What's the question? Sorry.
Sorry, I was confused. I thought you said that expanders were sparse.
Yeah.
But then.
We would like it to be sparse.
But a complete graph is an expander.
Yeah. Okay. This is not. Sure. I mean, the definition of expander is there's no universal definition. Yeah. People usually look at the problem and then they define the way they want to resolve the problem. But heuristically, we want it to be sparse to be useful. And lots of time, complete graph is not that useful. It's too trivial as a graph to study. Yeah. Okay. But here, the connection that I want to make about expander to these two problems, the cycle problem and the subdivision problem, we use a notion of expander that's not so common one, which we call, it was originally used by Thomassen and Semerdy back in the 90s. We can say it's sublinear expander. What do I mean by that? A lot of the expander in the literature, the expansion rate, if you look at the first definition, they require sets of moderate size, not too big, not too small. They grow linearly with respect to the set itself. Okay? And there is a notion of a sublinear expander. Definition is rather technical to write down, but roughly what it says is that instead of these, I require this to be, roughly speaking, x over log x, say. Okay? So I don't quite grow linearly with x, but almost. Let's put it in the simplified version. Okay, the full version is a little bit technical. But in the sense of embedding subgraph and short diameter, this kind of property, this expansion, even though weak, is still work, right? With a slightly weaker bound that you can obtain. And what's interesting about this version of sublinear expander is that they proved in their original work that every graph contains a sublinear expander subgraph whose average degree is almost as dense as itself. Okay, I can write it here. Every graph G contains a sublinear expander H with the average degree almost as dense as the original graph. Okay, this is proved by Thomassen summary. So what does that mean? Look at the two type of problem we're looking at. What we're given to begin with, we're given the average degree. And we don't really care about constant factor or whatever, right? So that means when we're given this type of problem saying that you have a graph with average degree, blah, 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 can you force some structure? We might as well hit it with this result and say pass through a subgraph that's a sublinear expander without losing much on the average degree. So again, we begin with a graph with average degree, but additionally, we have this sublinear expansion property. So all the results that we resolve here basically start with this basic sublinear expansion property, and then we go from there. We try to build some basic structures and try to put together them and to find the thing we want. So in the remaining of the time, I will maybe mention our main results and give you a very high level sketch of how possibly we can go about doing things using expansion. Okay? Any questions so far before we go further?
In some problem, we require that the chromatic number is large, right? And when passing to a sublinear expander, maybe we lose the chromatic number.
Then we cannot do that. We have, for this problem, it's more difficult. We have to do other things. So maybe if I have time, I'll briefly mention how we can do that at the end. Okay? In general, chromatic number is more complicated as a parameter than average degree. Average degree is very straightforward. Right, so this is recent work with Richard Montgomery. So what we proved, right, I don't want to bore you with too technical statements. Let me just say the corollaries. Okay, the corollaries. One is that this question that I wrote down earlier by Erdős in 75, asking whether 1/2 log d is the correct constant 1/2. So as a corollary, we can prove that 1/2. We can prove that the sum of 1 over L, you take all the reciprocal, is at least 1/2 plus little o log d of G. Okay, so this is true. We can prove the asymptotic type bound. And also this off-cycle problem, we can also prove it. Not just proving it, we can prove it with the optimal bound also. Here, what would you guess for the optimal bound? Anyone? Suppose chi of G is K. What would be the graph that you think minimizes harmonic sum? Complete graph, yeah. Okay. So if you look at KK, what cycle you have in here? You take all the odd one, is again 1/2. You take half of the reciprocal, right? So it's roughly 1/2 times log K, log the chromatic number. Okay, that's the strongest form you can possibly prove. And that's what we proved as corollary. So we show that the sum of L in fact, I will write down this weak one, but what we actually prove, okay, let me write down this weak one. Okay, log of chi of G. What we prove actually, this is just corollary. What we actually prove is not just odd one. You take any residual classes, then you look at its corresponding coefficient here in KK. For example, you look at 3, 0 modulo 3 or 1 modulo 3. Take whatever your favorite residual classes. You compute the constant, we get the correct constant there. I'm not going to write that more general version, but that's what we can imply. And for this specific sequence, we can show all this sequence. You can force indeed the power of 2 when your average degree is sufficiently large. Okay, and all this specific sequence. The answer is yes. Okay. And for the question of this Thomassen's cube problem, the answer is also yes. When the average is sufficiently large, then you can force a KT subdivision that's equally divided. But our bound is rather poor, something like double exponential in T maybe. But it's indeed so. Okay, so basically these are the corollaries. In the rest of the time, I want to hand wave some ideas that lies behind the proof. I want to convince you that at least we can sort of do that. Right? This is it's a subset of C of G containing all the odd numbers. The idea is in fact very natural, but the carrying out surprisingly quite technical, because this sublinear expansion is not additive. It could be that the union of some small set, they expand quite well, but if you look at every individual set, they expand very poorly because it's sublinear. It doesn't scale up. It's not additive. Okay. So, because if we know this, life will be a lot easier. But unfortunately, all we know by this result is a sublinear expansion. And you cannot guarantee better than that. There's a result showing that if you take a proper random subgraph of a hypercube, that's the best expansion you can hope for. So you cannot do better. So, idea, maybe let me just tell you how do you get some specific sequence, right? Let's just pick one. Let's see how we do that. So here's the idea. First of all, how do we use expansion property? First of all, one, expansion implies short diameter. What do I mean by that? That means if I have two sets X and Y you want to connect, we can do that using only polylogarithmic length path. Okay? The proof is very simple. You expand until it reaches more than half. You do the same from the other side until it's more than half. Oh, when they overlap, that means I connect them, right? So this whole process takes polylog in n step. Furthermore, this short diameter property is very robust in a sense that we are allowed to avoid some sets. Let's say we wish to avoid when we connect these two. We can do so as long as we touch every layer very limitedly, right? But as long as every layer still expand outside its red part reasonably well, then we can connect them. You have to quantify it. But this is the first basic property we will use. Short diameter, I call it short diameter property. Now, the idea of finding cycle of certain length is we want certain gadgets to be able to adjust length, right? So basic thing to start with is, can you get certain path of certain length? Then we close it up into a cycle of certain length inside this infinite sequence, say 2 to the I. So the idea here, very roughly speaking, this is the very basic gadget we can find. By large average degree, we know that we can force some even cycle, right? So this is an even cycle. And this cycle is small, polylog in n. Why? Because you just expand d. After log d step, you link it up and you do one more time. So log n, very short cycle. I take almost antipotal points. So that means the path here is length plus 1. The path down there is minus 1. I adjust it, okay? This is twice longer than this. Not twice. 2 additive longer than that, right? Now, I want to lead this out, okay? If I can find this thing, I chain lots of them up, almost antipoint, okay? Then I can change plus 1, minus 1, plus 1, minus 1. As long as this chain is sufficiently large, at the end, I close it, okay? Now I say, okay, it's not power 2, no problem. I have enough of these guys on the chain. I switch. You take plus minus 2, plus minus, adjust until you hit the sequence that you want. That's the very basic idea, okay? But then, let me just say a little bit more how we can carry out this idea. In reality, our sublinear expansion is too weak to expand these points away from the cycle. So what you really have to do is you take the antipodal point, you have to be able to attach a large vertex boundary, a large set. This guy has to be able to reach a large set, large enough compared to this guy, so that we can link. This is how we link in reality, how we link them up. It's like a candy, right? Where the candy wrap is sufficiently large, now we can use the short diameter property to find the short one, avoiding the middle guy, right? Because when we link them up, we don't want to touch the middle. This is, for example. So maybe I will not say more about the technical details. This, I hope, will give you some idea what to begin with. Okay, this is the starting point, and you do something. To answer Tuan's question, we cannot pass to a subgraph that's expanded and hoping that we maintain chromatic number. We can only maintain average degree. So this looks plausible to attack the average degree condition problem. What about the chromatic number? How we can go about doing that? How we can force out cycle, basically, right? Here we can only force even. So I'm going to say a few words about that. So here's the idea. This is my graph G with very large chromatic number. What do I want to do now? I want to be able to find lots of off-cycle, distinct off-cycle length, so that their harmonic sum diverges, right? So the idea is the following. What we can do is, large chromatic number implies what? I can find a subgraph that has large average degree, right? Just find a k critical graph, and that's k minus 1 degenerate. Large chromatic number implies that you have a graph that has large average degree. I make it bipartite, okay? And you take the edge set out. So I first take a bipartite graph that's dense, and I hit it with the Coleman similarity, make it sublinear expander. Yeah. So this is one edge set. Then I keep splitting out. I take this edge disjoint one, take it out. I can take this HI and look at the union of HI as an edge union. Okay, what do I know about this edge union? I can make sure that as long as I take as many as I can, the chromatic number of this edge union is large. Let's say 3. Why? If this is smaller than 3, then that means the remaining edges has large average chromatic number, right? You can just take the product of the chromatic number of the union and the complements. That's the chromatic upper bound for the chromatic number of chi of G. So that means the whatever we have not taken rest, they still have large average degree chromatic number. So you can keep taking out. So that means you can for sure reach this. Then what does that mean? That means this union of graphs, they are all, you can find all cycle of subgraph, right? You can find, I use this edge to represent this red graph. You can find, you have this graph, all different color. I don't know, something like this. Okay, let me make it simple. Just do like this, okay? You can find this subgraph, each edge represents a subgraph. Then I know this as union of the edge set, the chromatic number is bigger than 3. That means this graph of subgraph contains the off cycle, right? Like this. So now I forget about color. I just do like this. I contain some off cycle. Here's H1, here H2, H3, H4, H5. Yeah, that was nice try though. So H6, H7. Okay. Now what I do is that each one of these guys represent one of these things. Okay, I draw it like that. Now what I do is I just take some. I can prove that by some minimality. I can show that if they are not adjacent, they are completely vertex disjoint. Then just take a part of it. This one, and this one. By averaging, one of these, you can 3-color the off cycle. And one of the colors, say the red one, has large order. So you can replace. The idea basically, you can go around this by taking different color edges, right? Then you take the one that's most heavy one. You can replace the edge in here by path. Then you get different cycle length. It has to be odd, respect the parity, because this graph we start with is odd cycle. So basically, yeah, that's roughly the idea. Okay.
And this gives you the type cuts.
Right. Yeah. Yeah. Right. What we actually prove is that. Yeah. Let me not get to that. Yeah. That implies the type constant. Okay. So I think that I will conclude my talk here.
Any questions? Okay.
So can you do similar thing for the 3k plus 1 length cycle?
3k plus 1?
Yeah, like rather than odd. 3k plus 1.
Oh yeah, you can do any residue. Say you take any A and B, and then you look at any K. Sorry, you can take any A and B such that you let B R to be the residue, right? Okay. If this is my sequence, you take R to be N. You take any residue, I can hit this sequence. Yeah. And if you calculate the number, it will be the right number as corollary.
I mean, you need to have some parity condition, probably.
If we have chromatic number, then we don't need parity. We don't have local obstruction. Local coming from when you have average degree, we cannot force odd cycle. But now if you have chromatic number, you can force all sorts of numbers.
Both A and R are even, then no. If R is R, then A is even, then you can never force it by increasing average.
Average degree, no, you're right. But now we're using chromatic number. Yeah, you are right. Average degree, no. But if this result is here, I think Donggyal is referring to this one, right? For chromatic number, you can do that. Okay. So very last comment. This is also how we adjust the length to make the subdivision equally divided. You see the connection now? It's all coming from the expansion. We link this structure between every two branch vertices, and we make sure that there are enough in the between every pair to make them equally divided. Okay.
So what's the fastest growing sequence that you could write here instead of 2 to the I?
Right. So this 2 to the I is a power function, right?
Yes.
And our result implies that basically the limit is tower function, 2 to the 2 to the. So for tower function, you can force it, but anything faster than tower function, you cannot do it. There's an example. Okay, basically.
So wait, so doesn't matter how many. So what's the tower function?
Okay, let me write it down.
I can.
So what is 2 to the I? 2 to the I is basically says that sigma I plus 1 is at most some constant times sigma I, right? This is exponential function. What we prove is that as long as sigma I plus 1 is at most e to the sigma I to some power smaller than 1, okay? Almost like tower function, but not quite, yeah. Then you can force it.
Okay.
Yeah, so it grows a lot faster than 2 to the I.
And this is time?
If you change this to 1, then you cannot force it. Yeah.
What's the, is there?
Is it easy to describe a counterexamples?
Oh, basically, it's, let me see. I think you just do some gluing. You glue some graph with large girth and you keep doing that. Let me see how you do that. Okay, maybe I will think about it afterwards and tell you. It's not so hard actually. Now I cannot reconstruct immediately.
It's a tight result that you have there, in some methods.
Depends on how you say tight, so not quite. Yeah, not quite. Yeah.
So you only have
1/3, but the precise.
Oh, actually, we prove
1/10.
1/10.
But our method limit is 1/3 or 1/2. Using our method, you cannot hope to push to 1 because of this sublinear expansion. So we cannot push it to 1. Yeah. So maybe 1 is the correct one, but we don't know. Using this way is you cannot do it, right?
In this theorem about equally divided clique subdivisions, can you say more about the, like, can you describe the particular length?
Yes. So if we have an n vertex graph,
Yeah.
we can make sure that this length is some polylog in n. It's not so long. Okay. In fact, we link polylog n such structure, and then we link it up, right? And then you adjust this, so everything's within polylog. So the whole thing is not so large. We can make sure that it's relatively small.
It's as a function of the given the big graph, right?
The number of branch vertices is independent. The length is polylog in n, right?
How long is the proof?
I think the paper is 40 pages, 42 pages. Yeah. It's a little bit technical.
So this boundary that you get on the speed at which this function grows, do you get a different bound if you instead go to chromatic number?
Weaker bound, in fact. Because chromatic number is more complicated, we have to do this additional argument. So for chromatic number, we only get this growth. And that's a good question. It gets weaker. But this growth is enough to get what Ben was asking, the tight number. Okay?
Chromatic number then.
Already. Oh, okay, because you don't have. So it's not sufficient to have this growth. You also need to have this growth intersected with even numbers. Okay, I see. Right.
Good. You answer your own question.
I'll just do it if you have big growth.
I like this audience. I don't have to answer questions.
So these two theorems on top, like if you restrict the graph to be like triangle free, for instance, then can we expect to have a similar theorem with the better constant on the right hand side?
Oh, that's a good question because 1/2 is tight for the clique, right? So if you forbid triangle, I don't know actually. Yeah.
The 1/2 maybe you have.
For the second one, yeah, I don't know. maybe you can get.
So you can consider complete bipartite graph and connect it by some path, so that all the odd cycles are using this path. But you essentially get every odd number bigger than the length of path.
But why your chromatic number is large?
Chromatic. No, sorry.
But the average degree is large in that case. So
Maybe you can get better. That seems more. Yeah, that seems quite. Yeah, I don't know.
okay. Any other questions? So if not, let's thank the speakers.